Hi, welcome to the next video in our course on Intro to Material Science. And this video is going to be on crystal structures in 3D. And we will also see how ideas such as Miller indices for crystallographic planes and directions work out in 3D. We have seen these ideas in 2D lattices earlier, and those ideas extend in a fairly straightforward way to 3D as well. And before we take the plunge, we need to distinguish between crystal structures and crystal lattices. And as you can see in this slide, the crystal structure is defined essentially as a combination of the crystal lattice and a motif. Motif is a fancy word for a bunch of atoms or molecules, and this bunch can be quite complicated and messy, especially for crystals of importance in biology, such as proteins. You may recall that the ribosome molecule has nearly 500,000 atoms, and those molecules can be quite complicated. But we will be focusing mostly on fairly simple crystal structures that are obtained using the simplest possible motif, which is basically just a sphere. So in the above cartoon that we have shown here, I have used only a very simple motif, a triangle that represents a molecule. And let us now turn to a real crystal in 3D. The simplest motif, as I said, that one can imagine is a sphere representing an atom. There are quite a few examples among elements where the atoms do appear to be like spheres, tiny spheres. Metals such as aluminum and copper and noble gas elements such as argon do appear to have their atoms in the form of tiny spheres. So here's a simple cubic structure. So you get the structure by placing basically a spherical atom at each lattice site of a simple cubic lattice. Among the elements, only alpha polonium has this crystal structure. In a similar way, you get a BCC crystal by placing a spherical atom at each site in a BCC lattice. Quite a few metals crystallize in the structure. I've given some examples here: alpha iron, beta titanium, chromium, vanadium, niobium, molybdenum, and so on and so forth. Finally, you get the FCC crystal when a spherical atom is placed at each site in an FCC lattice. Solids of many elements have this. Structure. Examples include metals such as gamma iron, nickel, copper, aluminum, and examples would also include noble gas elements such as argon. A key characteristic that you are all familiar with is the number of atoms per unit cell. This table summarizes the results for the three cubic structures we have discussed so far. A simple cubic structure has just one atom located at the origin, whereas the body-centered cubic lattice has two atoms, one at the origin and one at the body center, which is at the halfway mark along the body diagonal 1, 1, 1. Thus, its location, the location of this body center position, is given by the position vector, which is now expressed in the crystal lattice coordinates as 1/2, 1, 1, 1. Finally, the face-centered cubic structure has four atoms, one at the origin and one at the center of each of the three cube faces that run through the origin. Since the face centers are at half the face diagonals, their locations are given using this fractional coordinate system, using the position vectors 1/2, 1, 1, 0, 1/2, 1, 0, 1, and 1/2, 0, 1, 1. Now let us look at the arrangement of atoms in these structures. Essentially, we find that the atoms are lined up, that is, touching each other along the cube side in the simple cubic structure. On the other hand, the atoms are lined up in contact with each other along the body diagonal in the body-centered cubic structure and along the face diagonals in the face-centered cubic structure. This implies that the side A in the simple cubic structure is equal to 2 times the radius of the atom. However, if you look at the face-centered cubic structure, you see that 4 radii are packed along one face diagonal. And in other words, the face diagonal, which is basically the square root of A, is equal to 4 times the radius. This allows us to compute the packing fraction in these structures. I'm sure you have done this earlier. Here are the results. And I would like you to check and confirm these results. So let us now turn to planes and directions. As we saw in the case of 2D lattices, the Miller indices are given in terms of the basis vectors. For example, the 1, 0 is a direction which is along the A vector, and the 0, 1 is along the B vector in the crystal lattice. Similarly, in 3D, we have exactly the same sort of definitions. So here are the 1, 0, 0, 1, 1, 0 and 1, 1, 1 directions in a generic 3D lattice. And so we finally we turn to planes, and when in the case of planes in 2D lattices, the first of the HK family of planes has its intercept at A over H along the A axis and B over K along the B axis. So we implement the same idea in 3D. This picture shows the 1, 0, 0, rather 0, 0, 1 plane. Note where the origin is. The top plane is 0, 0, 1 with respect to the origin as defined in this picture, and the other planes are drawn using other lattice points as their origins. Similarly, here is the 1, 1, 0 plane, in which again you see the first plane with respect to the origin which is defined in this picture, and the other planes are drawn using other lattice points as their origins. And finally, the 1, 1, 1 plane in a generic 3D lattice is also shown here. As we will see in the next video, which will be on atomic arrangement of atoms the atomic arrangement in various planes. Since atomic arrangement along different planes and also along different directions is different, crystals also exhibit they can exhibit different properties along different directions. And here's the atomic arrangement of atoms in a 1, 1, 0 plane in FCC structure. And here's the arrangement in the same plane, 1, 1, 0 in the BCC structure. And as you can see, the atomic arrangements in these two structures are quite different. So this is across crystal structures. But in the next video, we will also see the differences in atomic arrangement in different planes within the same structure. And we would like to be able to say certain things about such arrangements. So with that, let me conclude this video. And so we will continue our discussion in the next video on these topics. So thank you and bye.